Hi, folks. I am 王不老说半岛. Today, I'm going to give this class some of the material in English under a reader's request, and then I did some modifications to add more content and try to be more comprehensive in this topic. The topic is manufacturing and process optimization for GaN, especially focus on the E mode. How do you make a PGAN, which intrinsically a D mode, depletion mode, into an enhanced mode, in terms of especially focus on the defect and also on the and why people do that and how to solve that with process. And this is the focus of my talk. And I try to on the fly to use some common AI tool that I've been using and which I enjoy a lot. There are two AI tools I like to introduce you, Connected Papers and Perplexity AI. These two are one of the two best I have seen right now. Hopefully there are more good ones coming out, and then we can all benefit from it. And let's go back to the topic. So as I mentioned before, uh, this is a review of the previous topic about the high two deck two-dimensional electron gas. What's good about it? What's good about the material or device has very high 2D gas. 2D gas, 2D electron gas, meaning that your ion can be very small. But once you turn on, boom, you got a very nice low ion. Look at the graph on the right. The GaN ham can have this very, very low, all right, the RO. And this is critical. It's much lower, can be than silicon carbide or especially silicon. And people had used this RO and then come out with some kind of benchmarking graph, which is RO. Check out the unit, ohm centimeter square. This including the area effect. So this is called specific, a specific ohm. Very critical for you to understand that does it mean by specific, meaning that it already removed the effect of surface area. All right. And if you want to get the real ohm, the real resistance, you have to divide this number by the area. That's how you're going to get it. And the versus the breakdown voltage, which is a key parameter. So RO versus the breakdown voltage are the key two parameters. And this is the best in class a comparison of all the material devices. Make it very clear. Okay. And so the GaN can operate very high frequency at very high voltage with low power. This means that the RO is very small, right? Then that you could avoid very consuming a lot of power. That's what it's trying to and that's what it's trying to say. Oh, very nice. Of course, but it has problems. What's bad about having a high 2D gas then? Well, you got to pay the price. That's how nature works. There's nothing free in this world. It's a normally on device. So you leak like crazy. If you look at this, when gate voltage is at zero, it already had pretty decent dry currents, drain currents. And that's not what you want, right? Because you haven't asked him to do something yet. And you start to leak. And that means there's wasted power. Okay. And that's no, right? Of course, as a deplete device sometimes has some benefit that you want to capture. That's true, but that's not in this case. Okay. And here we like to push to the right hand side. What it means that the IDVG curve, you know, this curve, we want to shift to the right in a way so that when gate voltage is zero, you got almost zero leakage drain current. Right? That's the purpose. And then I put a reference here. The reference here is called the white paper the Panasonic white paper. So what is a white paper? Let's look at it. A white paper is what, you know, the industry will publish about the technical detail of their devices. See, this XGAN is what Panasonic is selling. It's on the market right now. The spec says that it can control is rated about 600 volts. So it can control something with 600 volts with pretty decent dry current. And it's a GaN device with a injection transistor. The GaN injection transistor. We will talk about what does that mean later. So it's good for you to go through this one. Why trying to sell you? Of course, it always says good things about your devices. And here we're going to focus on the current collapse today here. Okay. But it's good that you in this field, at least you pick one to study thoroughly for each page, what it's trying to say. Now, overview, advantage, and then here, this is a picture I copy from, right? And this is the left-hand side is the device actual physical structure. It starts with the silicon 111 substrate. You can see that. And then do LGAN and do aluminum nitride as the nucleation layer, which we describe in detail in other video that I published on this topic. Basically, what it means that you see, this is silicon. At the end of the day, you want to get gallium nitride, and you are swapping everything at the same time. You are swapping silicon with GaN, and then you're adding nitrogen. That won't work. Just won't work immediately. There's no way you could deposit gallium nitride on silicon carbide, on silicon 111 directly. The reason being, look at it. Gallium melt. What's gallium? It's a low melting temperature material. It melts about 30 degrees. And silicon melts about 1500, 1444 to be exact. Then 1414, and so it's not compatible. Right? And you're talking about not a CVD process. You're talking about epitaxial growth. You need them to bond one by one properly. And there's no way you can do that directly. Aluminum come to save the day because it's quite sticky. Because aluminum is a very strong oxygen getter. So it will remove the surface oxygen from the silicon 111 and then start to adhere on the surface and you start to nucleate, right? And introduce nitrogen at the same time, form very strong aluminum nitrogen nitride bonding, super strong in nature. It's a super strong nitride. And then you start to add gallium into it. All right. Now you change its lattice structure slowly. And then you go to this so-called super lattice. This one because you are going to have tons of defect. I'm talking about tons of defect. And that is unavoidable. This tons of defect going to go up. Wow, it can go up. And then you want to divert it with these strain relaxations. And you want to divert it off with this so-called super lattice buffer, which I have also discussed that in detail in another topic that I have on this subject, pretty much the epitaxial growth of gallium nitride on silicon. Okay. And after that, eventually you could build your gallium nitride epitaxial on top. You're swapping it, look at it. You're adding it and then removing it. Once you go through this, eventually you remove the aluminum. That's not what you want. You want gallium nitride. Okay. So that pretty much summarizes a quick summary. And this one, and then so you go through this and it will give you many good things about the technical detail about this material. Here, the QRR is very important, right? It's 56 nanosecond, and then Coulomb, and then 10 micro. And this is how fast the material responds. The smaller value, the better. Okay. And this is a physical structure about the device structure, which we're going to discuss later on, right? You have the PL GaN, and then this is what's happening, and then you're gonna this is the old structure. What about the new structure? Okay, so that one they will introduce one at a time, and then the P GaN here. See, they have split the gate into two. What? conventional versus a hybrid. This is one they're selling. Okay. This is not good enough. They need to do some work. Okay. And then the why they want to do split the gate into two. You're consuming area, by the way, right? You're adding more here, the drains here, and you're adding another peak as a drain here. Okay, besides the gates. And there's a reason behind that that we're going to talk about. And the JIT, the JIT reverse recovery is much better, right? They could make it 39 nanocoulomb, which is much better than the silicon. So this one, the response time is much better. And that's the advantage of GaN. And maybe that's the reason Elon Musk say, I want to do this. I don't want to use silicon carbide unless I absolutely have to do that. So he cut down 75% of his EV devices. Silicon carbide, he removed 75% of them, only 25% left. So you better go through this material, all right? Here we're talking about, okay, reliability. That's another topic that to be covered. That has been covered by my other video. If you're interested, let me know. Okay. So anyway, this is good stuff. Bottom line, go read it. Okay. And then you don't get this feel, go read it word by word until you understand every one of them. Now you got a good standing point of your further study. Here in this talk, we're focusing on the current collapse phenomenon of a GaN device. But what I mean is that when you keep operating the device, everything hunky-dory in the beginning, right? No problem. But as time goes by, you will see, oops, what's going on? Your current gets lower and lower. As if something resistive is happening. As the device is more and more resistive, this means that the ROM is increasing slowly. All right. That is the problem. Then you ask yourself, why this is happening? Right? If you operate, you have a device that working great in the beginning and then deteriorate pretty fast. Then the current you put out is less and less under given voltage. That's not acceptable. It restricts the output power of the device. All right. And later people do some study, of course, they find out what went wrong because the trapped electrons. The drain started, when the current go through, the electrons should go through like great, like smoothly, but it didn't, it turns out it did not. Some of the electrons have been trapped. Somebody take it and hold it. All right. It's the trap charges at the bulk and then at the interface and the barrier. It's everywhere, pretty much. Okay. But then why is that? Why electron trap there and will not just go through properly? And that is the study. And then people did not understand it until even recently. Okay, recently. And then this is the paper just published last year, right? Pretty comprehensive. At the end of the day, this is what happens. They say, okay, the trap charges, the interface trap, no matter what trap you're talking about here, it could be everywhere, pretty much. You create a virtual gate. A gate means something. Gate means that it's modulating your current. And that's what gates are about, right? Gates try to control. You want it on or off. The source go current, the electron go through. When you say on, the gate say on, open the gate. And then the source will drive all the current to the drain because the drain voltage attract current go through. That's what you want, right? That's why it's gatekeeper here. But there's a hidden gate beneath the gate, and it's uncontrollable. You don't know, it's just there, and you don't know how many current can control. So this So this is what it means. So I use the Perplexity AI to to explain. Say, what do you mean by virtual gate? I don't understand. Can you help? Of course. This is what I did. So I opened Perplexity AI and I asked this question, right? What does the means? Uh, what does the virtual gate mean in the current collapse model of Kent? When I type that in, this is what it answers. Pretty clear, right? A virtual gate is a negative surface charge, negative surface potential behave like a negative bias metal gate. Okay, that's what it means. And then this, it's easier than I go through the paper and try to study it. You know, these days you need a Perplexity AI to help you, and because one paper may explain something you don't understand, and then you could use this tool to see, oh, see, there's multiple sources that help you understand. These one, two, three, four, five reference for you to go ahead and understand. You could click them. You could click them, and it tells you, what this paper is coming from. This is another old paper, virtual gate. All right. And that, okay, yeah, you could download the paper through your school website or search the web. Sometimes the author would just publish their paper on web for everybody to explore. That's the beauty of this. You see, Perplexity AI did a good job by summarizing all the real reference. ChatGPT sometimes go crazy and go nuts and give you wrong reference, but not Perplexity AI because Perplexity AI, the way I see it, is combine ChatGPT with Google Scholar. So that's the reason they did a better job. The new version of ChatGPT may do pretty good. All right. I think that everybody's trying to compete with each other and let the best win, right? That's good. Nothing wrong with that. Right. And then oh, okay, now I think I got a better grip, better grip of, about the what virtual gate means. I think the bottom line is virtual gate is fine, but as long as you can control it, it's fine. You can use some method to mitigate it. Problem is that it's not controllable. You don't know how big the virtual gate is. If you knew, you could use some other trick to mitigate it, right? But it turns out it's uncontrollable because you don't know what the defect, how many defect there. Unless you say, oh, can I eliminate all the defect? Yeah, if you could do that, yes. Then you don't worry about what you get, right? The problem is that, okay, it's difficult to remove the defect. And this defect is called defect center. Okay, they call TX center. Okay, what they mean, we can go after later. Before we move away from these page, let's look at this paper by itself. Okay, I use so-called connected papers, this website, all right, to study this paper. Okay, this is what I meant. So I copy the title of this paper. You could do so. And then this is what I did. This is the connected paper website. So I copy and paste, and then this is the paper. And then, okay, they found a paper, and then I click it, it generates a graph. It generates a nice cloud graph. It's called the bubble graph, right? It is the size of the paper, meaning the importance, which means the reference, people refer to it. And here, 2023 is this size, not as big as the Kumhara paper, but it's okay, it's getting there, right? And then this is the paper that refer to it, all right? Now refer to it. And then here is a relevant paper that they think they are linked as well. And they have all these, late paper, okay, earlier paper I meant. And you can see that these are at a deep color, a lot size color. And then here you see this paper, uh, it has PDF connect to it. Wow. See, that's how come got this paper for free, right? He had this paper. And then this is a picture I copied from. Isn't that nice? And of course, you could do other ones. How about this one? This one is on the left-hand side, right? On the left-hand side. And this one, wow, it also has a PDF. Okay. You could actually, okay, we're not going to open it, but you know what I meant. And you could open the graph. You could open the graph and then use the new paper. Okay. I waiting for a server. Okay. It take time to build a graph because searching all the database and trying to build a graph for you about the importance of that graph, of that paper. Once you make it, all right, and you could start to see the importance. I would say the convenience of this paper, all right, and then this is probably a very important paper, and it would take time to build it. Wow, check it out, check it out. All these papers like that refer to this paper, or he referred it other paper, and this refer over the other papers connected all the way through, right? So that help you to do your study. Isn't that great? Great. I remember when I was a grad student at Berkeley. I mean, when I got a good paper, I did so much work trying to get a reference paper right, and this take me at least a couple of weeks to get this type of research done. And right now, it's at your fingertip. All right, that's beauty. It's just beauty. And okay, so I introduced how you use connected paper and Perplexity AI to help you to further your study. So we'll come back to this topic. And then here is all because so-called defect center. DX center, defect center. All right. It's a deep trap center. You could call that. Okay. The DX, D means deep. X means you don't know what it is. That's what I meant. Okay. And then X means, it's oxygen vacancy, which inside the nitrogen site. Okay. The problem with 3.5 and then no 3N, whatever. All these are because things are still in the wrong place. At the end of the day, is thing the element are not in the right place. And when they're not in the right place, oxygen in the nitrogen side, and then this is alien matter coming in. Remember, all the 3.5 and 3N, they are dirty. There's a lot of oxygen inside. It can't get away from oxygen. You say, even though I don't have oxygen here, but no, you do, because when you're manufacturing it, oxygen is coming in with a small amount. Okay. But how small? Well, 10 to the 16 to 10 to 17 gonna kill you. Okay. Already. And that's a problem. And there's no absolute clean environment. Even outer space is not clean enough. Oxygen is simply everywhere. And it's so difficult to get rid of it. And the silicon O2 is so good because this oxygen in silicon is very, very low. But even so, they have a problem. Okay, even so, that problem. And so here we're comparing with the PB center of the silicon and silicon dioxide interface. Deep center means that it's everywhere inside. Oh God, that's the problem, right? It's not just at interface inside. Pretty much the 3.5 and 3N are naturally very dirty. Okay. Dirty means difficult to remove deep level defects. Okay. Passivation, there's a lot of passivation schemes that people try to say, oh, I'm going to dope it with this. I'm going to heat it up in this, in hydrogen, in deuterium, in nitrogen, you name it. They say, I will try to reduce the defect. But none of them can reduce to a level that is very satisfactory up to now. Okay. And then the deep level, and it's also functional aluminum. The energy position will be different. There's adding more complexity. And why is so defective? Okay, and we could look at this Stanford report. Let's talk about the 3,5 gallium nitride case. The same case apply to gallium nitride or anything, right? We will find out that at the end of the day, that they find gallium nitride has very deep level. So deep level means that in energy away from the conduction band and valence band. It's inside. See here, it's zero point 0.5 volt below above valence band, and then this here is about also close to zero point 0.5 volts, zero point 0.4 volts, yeah, or more below conduction band. There are two peaks there, and there's no way you can remove it. Okay, why is that? Because these are kind of an anti-side defect, means that arsenic is the wrong place. They are putting they when they somehow go into the gallium side, or vice versa. Okay, so these sides, all right, is one of the theory, of course. So they have anti-sides here and there. These two are the most famous one, zero point 0.5 volt and 0.75 mole, and 0.75 electron volts. These arsenic in the gallium side. So it is a form why you're forming gallium arsenic crystals in very small amounts, but that small amount enough to kill you. And you say, oh, okay, I'm gonna do something to mitigate that. Well, there's nothing you can do. Very little can do. You put some hydrogen, you put some nitrogen, you put some everything, and no matter what you put it on, you cannot change the andesite nature of this crystal, right? To do something to cover it up. But pretty much you cannot really change the nature. And that's why there's no gallium nitride, I'm sorry, gallium arsenide device not working properly. As a CMOS, you could work on something else. But as a logic, it simply won't work. Because when you have this type of defect here, and if your formula level is moving around this here, then it won't work. You will be pinned. Your formula level won't move. I later explain what formula level pinning is. But right now, formula level need to move around at the interface, and then it will not move. And because there's a defect here, it's going to kill you. It's going to suck up your electron charge, right? And that's not good, right? And if you put that into gallium arsenide, I mean aluminum GaN, had the same problem. Not exactly the same, but similar. The crystal defect inside the crystal, they have a lot of deep level defect, and these defects uh, is very difficult to remove. You can cover them up to some extent, but you cannot really remove it. Nobody can do that yet. Okay, and so that's the problem. And so okay, so now let's segue to PP center and the band bending. I want to segue out a little bit so you understand uh, what I meant by PB center and the band bending and what it called the fundamental level bending issue for device. If you look at this report, you can see that PB center people this got called a defect in the silicon and silicon dioxide interface. They are just broken bonds, right? Broken bond, different type of broken bonds, PB, PB0, PB1, and we are running out of names to name what we find out. So we come up with those strange notation. So bear with us, okay? It's a amphoteric. It can be positive or negative charge. How can it be positive or negative charge? If you look at this, all right, and then you look at the band bending here, if this is positive and this had to be negative, this means that because need to be balanced. Okay. If this is negative, then this has to be positive because overall charge has to be neutral. And that's pretty much what it means. And how it works that way, I have I will discuss that a little bit in the subsequent presentations. So pretty much that the Fermi law is interacting with PV centers. Okay. And when you interact with it, if these PV centers, which means in a layman term, is that is eating up your charge. Fermi level is somebody, and the moving on the Fermi level, the band bending is somebody want to, especially your applied voltage, want to induce the band bending. That's the purpose of applied voltage. Because if you bend enough, if it's sometime at the end of the day, you will invert it. At the end of the day, this is what you want. You want the band to bend because of applied voltage. If the band does not bend, you're in deep trouble. Then device is not working. And but when you bend, the surface, the interface come to play as well. And that's where these defect coming in. Defect say, no, 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 no. You want to bend? That means that you're accumulating charge here, and now I have to do something here. You need to pay me with some charge. Okay. And that's what it means. And that is not good. Okay. We don't want to pay. If you want to pay, you don't have enough energy to do the bending here. Okay. And their silicon defect density is very high. It's to E to 14. Remember, the atomic density of a silicon surface is 10 to the 15, roughly. It's 6.8, 10 to the 14, right? So if you have 10 to 14 means that 10% are defective as a broken bond, and that's not what you want. But if you put an SiO2 there, yeah, they have order of magnitude less. That's the beauty of silicon SiO2. On top of that, you say, I'm going to feed you with some hydrogen or deuterium, deuterium, T2, then your defect density go to E10. Wow. From E14 to E10? Yes. And that's why silicon device worked. It's E10 everywhere. If you can make that happen, you have a larger device, P and N both work. But 3.5 won't do that. You could do one side, but you can never do the other side. All right. It's always remain very high on the P FET. Okay. The M FET probably okay. You could tweak it to about E10, 11, but for the P FET, there's no way you can make it work. And that's the reason there's no logic GaN device, GaN arsenide device. Okay. Same thing with GaN nitride. It just won't work because the defect is everywhere. They go a little bit deeper. This is the PV center for silicon and silicon dioxide. And basically, it has a defect at the center, at this interface. And where that defect come from? Is it because people think it's called the mix, this gap state, the metal-induced gap state? When you put something on top, it will change the interface. All right. People did a very complex density of state calculation, and we're not trying to bother you with the details. It's too much. But I would like to give you a visual understanding. Okay, it pretty much is that when the metal come into contact, it will hurt at the interface. See, I was joking. This is a knife. You know, the coupling of the metal to the semiconductor, you go and hurt the inside. See here, the nickel. You got that silicide going to different interface, and you can see that this bright spot. This is the wound. You can imagine it's a wound created by the metal. Because the metal density of state, they have a lot. They'll come in and destroy you, and it did. Okay. At the end of the day, is what happens. The charge is supposed to be induced by the V gate. See, not virtual gate, the applied voltage, gate voltage. That the purpose of the V gate is to induce charge, to bending. You know, that's trying to do. You want to get as much of charge as possible because you need to invert. Without enough charge, you won't invert. But with this defect inside, you had to this kind of highway robber, right? The charge will go there. Some of the proper charge will be stuck up there. is not going to give you to the band bending, and that's not good, right? So it means that the gate control is now less effective, right? It lost effectiveness in controlling the surface potential of the interface, and that's not good. And why this is happening? People have done so much work. Okay, this paper even mentioned that they form a specific layer called interface specific region, ISR. And here, the reason pretty much this. The metal, when there's the block wave coming here, right, is interact with this, right? And then the Fermi level, and they try to interfere with the Fermi level, also the energy band gap inside the semiconductor. And this region is kind of wacky. Nobody knows exactly what's going on inside. It's so messy, right? Because what happened is that metal can mix up with semiconductor. They're not perfect. They're abrupt, but they're not perfect. They could be in a mixed. So nobody exactly know what's at the interface. And by the way, there's a lot of oxygen coming into play as well. And then some researchers even believe it creates some kind of quantum dipole inside with a lot of very large electric, very weird E field. Right? Let's not go into the detail. I just said that the interface is messy. Okay, and let's go back to device. What the device try to do? If you look at the device, this is the oxide, the metal oxide semiconductor, right? This is your oxide. This is your metal, and your semiconductor. And when you apply a V gate, apply voltage, a gate voltage, you try to control. What are you trying to control? When you, the first thing that we do is to push the Fermi level of metal down. When you apply a positive, this is a positive, you push the Fermi level down. All right, and the higher and higher we get, the deeper and deeper the Fermi level going to move down to. But the Fermi level inside semiconductor will not move. It can only move by the doping. Once the doping is fixed, the position of semiconductor is fixed. The position of this Fermi level inside the semiconductor is fixed, which means that this distance is fixed. This distance is fixed. But that's not going to work properly in the base, right? So in order to maintain the charges, the band bending has to occur. So the bands start to bend. Right here it start to bend down, because it had to follow this. And then the more you bend down, see the bend, because you have in a way depleted the surface, all right? And you have ionized acceptor here. And then the more you do until something happens, and something happen in a way that it bend too much. When the band bending, when here become 25B, right? This is a basic CMOS, how it works. You have inversion. We describe that if it's greater than the 2x of surface potential, 25B, then it will form electron to the gas. Whoops. Wow. Nice. So what's the benefit of forming to the gas? Well, your resistance go down, right? That's where your R is. Remember? Right. High 2D gas, your R is very small. That's what happened here, even in silicon world, right? Even in silicon world. So this, and then that's devices, boom, on. And when it's on, then that's what you want, great. And then you put the VG off, maybe you become, you lost that, it coming back. And that's exactly what the VG is forcing, was trying to do. It's forcing the ECEV at the interface to bend, okay? But what do you about Fermi level moving? Well, I'm sorry to say, but Fermi level never moves. It never moves. It's always here, right? The distance between the Fermi level inside the semiconductor is moving. Okay, it's not moving at all. The Fermi level on the metal side is always moving, very effectively 1 volt to 1 volt by the applied voltage, and no problem obeying the law, obeying to the applied gate voltage. So what do you mean by Fermi level moving? It's because if you sit now, if the observer is sitting at the band edge, all right, then you see your Fermi level is moving towards you, right? Here, see that? It was here very far away, right? But and then when you go more and more, the band bending further, the band bending is closer and closer to the Fermi level in the semiconductor side. Imagine you are sitting here, then you will see the Fermi level is moving towards you, isn't it? Here you're seeing closer and closer, right? In effect, it's you are moving. You're sitting at the band edge, you're moving. Fermi level never moves, okay? But for convenience, it's difficult to fathom, right? So we put observer here, then we'll see Fermi level is moving around, okay? So, and it's difficult for a device guy to explain that the observer is on a Fermi level. So we put it on the other side. We interpreted the whole thing by shifting observer to the edge. And then he sees the Fermi level is moving toward away from him. So Fermi level is now moving, okay? The Fermi level, so this explains what people say that Fermi level pinning because bend is not bending. That's what it means. And you can use the surface potential versus the surface potential versus V gate. The data delta, if you apply voltage 1 volt, the delta VG 1 volt, then we want this to bend 1 volt. All right, that's the purpose. That's what we hope for. We don't lose energy while we are applying voltage all the way to the band edge. But the ISR said, no, I'm not gonna let you do that. Okay, because I have family to feed. I have defects. Okay, you gotta pay me. In that way, the charge has been stolen. And so the 1 volt, you apply 1 volt, but the band edge may not get 1 volt, maybe get 0.8 volt, 0.5 volt, who knows? It depends on how severe the ISR gonna rip you off. Okay. So this is not the applied gate voltage is not as effective as we like because it stole the charges. Okay. So that's one way of looking at it. The other one is looking at S factor. The Schottky barrier height, okay, of your contact when two material contact each other, and then say metal semiconductor. And then you apply a work function metal, and you can see the change of that. I apply a work function metal if I change 1 volt, okay, from 4 volt to 5 volts. I want your Schottky barrier height to reduce the same amount. That's ideal, right? I want you to change to 0.4 volts, I say here. Okay, 0.6 volt to 1 volt, right? If you're going down, fine. Say, well, go to 0 here, it won't work. All right, here, here 1 volt, but it did not. See, the slope is 0.16, meaning that you you give me delta 1 volts by work function, I want to give you 0.16 volts into the Schottky barrier height. Wow. I give you 1 volt change, you get 16%, right, of that 1 volt. Say, well, until you see silicon germanium, you got 16% is pretty good. You got ripped off. But yeah, you got ripped off for 84%. Consider that good. You look at germanium. How much left? Nothing. 3%. Everything is going to respond to your metal work functions. So if you had 55% or 45% germanium, you see cut by half. So this is called S factor. It's comparing Schottky barrier height versus the delta Schottky barrier height versus delta of work function metal, your work functions. And that's another measure of the effectiveness of applied or function metal or apply K voltage. And here's the biggest challenge on that. This is what is called the Fermi level pinning. Okay, that's what it means. Now let's segue back. Okay, now let's segue back. Okay, the purpose of this talk is to describe how do you uh, modify an intrinsically D mode p-ham to an E mode. The Panasonic suggests they use so-called gate injection transistor. Okay, and this is what it's trying to say. It was without the JIT. Conventionally, is what happens. The reason you have this normally on because the Fermi level, see the band bending, all right, it occur uh, naturally. It bends naturally inside a PGAN. PHAM is normally on. And this is why it's 2D gas formed by nature. We have a full video describe why this happened. In one word, because algan is strained. It forms a specific dipole, all right? And then this dipole, if your proper configuration, algan on GaN, dipole will attract charges and start bending here. So the EC band, when it bend reference to the Fermi level here, it bend too much, then you would induce the 2D gas by nature. And so this we explained thoroughly here, than in our video. But here, how do you turn it off? Then you by adding a metal, begin here with a doping. Okay, begin here with doping. And why want you to P? Because P doping is very close to the band edges. You cannot use N, right? N doping is here. And when align all your semiconductors, their Fermi level has to be aligned. That's the nature, right? And we have a full video describe why Fermi level has to align. Okay, and let's say okay, all these three semiconductors they have to align. Okay, even metal, right? The outside metal has to align. Everybody has to align unless you apply voltage. When you apply voltage, the metal Fermi start to change, but nothing changes inside. Still, it's the Fermi level inside the semiconductor. All these semiconductors, they still has to align. That's the beauty of Fermi level. So it's so low here, right? So what it meant is that it pushed this one up. It pushed the algan Fermi level up. Okay, it pushed way up because the bottom has to align here, right? And here is, let's say, some kind of medium doping or no doping. Okay, so the medium here all has kind of end doping, so it's close to the ECH initially. But now, whoops, you have to force everyone up. Then here is no longer band bending. Here it goes to here. Okay, no band bending anymore. It bends in a way it's far away from. It did not form this proper insertion of the band edges across the Fermi level. If you do that, then you form a 2D gas in some uh, in some conditions. Here you put this ECH away from the Fermi level. You are not going through. You are not bending across the below the Fermi level. You're not make it happen again. So that means that oops, you no longer have 2D gas, and that's what it meant by normally off. Right, you cannot form 2D gas, so it's normally off. Nothing is working. Nothing is charge is not accumulating at the zero voltage. So this edge, so the algan GaN band edge is forced to lift up. It forced to lift up because this one goes up. The Fermi level is being forced to be low in the PGAN because you have a P, right? P means that you dope your primary level in a way that is very close to the EV side. It's very far away from the EC side. And that's what the peak doping means. And everybody has a line, then everything else lift up. And that's the bottom line. Okay. And we have that detailed explanation in the other video that I published on this topic. Okay. So what's the difference between enhanced mode versus depletion mode? Okay. The depletion mode is that the current go through when the cable is zero. And you need to do something to turn it off. You need to spend energy to turn it off. This could be good. I mean, sometimes you want that, but that's not what we want. And then the enhanced mode is that if I don't ask you to do anything, don't do it. Okay, then that's what it means. It's no channel. So enhanced mode, depletion mode is basically if you are inside a channel, if you see a current flowing, then it's the depleted mode. If you see that there's nothing flowing, then that is enhanced mode. Okay. So what do? You want to turn it off. So okay, you want to apply voltage. Okay, I'll give you apply voltage. So classically, that's what people do. They add another low voltage silicon MOS to stop it. Oh, it's okay. I mean, that's how it used to work, right? But you're adding another silicon CMOS, silicon MOS, it's costly, right? You make a new device, or you physically adding a silicon MOS. It's not built on the same device, right? It's external device. You connect them in series, and thus you make it normally on from a normally off device. And that, of course, costs you real estate. That costs money. Right? You need to buy these small things. And then on top of say, okay, I have money, I don't care. But well, wait a minute. It's not going to work at high frequency, right? Because there's an external device, the coupling, that make you have to respond. You want everything to happen at the same time for the high frequency to work. Then with external silicon MOS, how do you know going to respond as quickly as you can? You know, silicon MOS is actually slower compared with your CAN device. I said, oops, that's not good. Okay, so we need new ideas. So this is what people think, right? Then that this is how that works. Basically, on every different voltage, you can see that the gate controlling. Gate can be LGAN gate, can be PGAN gate. It depends what you want to do. It's easy to figure out what you need, and that by simple simulation. People do this by simulation. But pretty much when the V0 is zero, nothing is on. Okay, that's what you want. And then when is that good enough? Maybe, maybe not. Okay, so pretty much this is initially what people think you can do. Okay, but and here I would like to introduce a concept, the so-called the transconductance as part of the device that people think when you go over, see here is a little bit, this is a normally off device, all right? Then when the VK is zero, and this is what you normally is, but it turns out, you look at this curve, this is your ID VG curve. You take a derivative of this curve, this is what you get, this is called transconductance. It's a reverse of resistance. Pretty much means that what is the boat, how sensitive is your B gate change in terms to cause the drain current to change? See, if you change 1 volt, then how much drain current will change? Let's look at this picture. So, okay, 2.2 volts. And then if you change to 3 volts, and then you got this is what you're going to get. Okay. 3 volts here, sorry, here and here. 2 to 3 volts, you change like 40 to 100 milliamp. conductance. Is that good? And that's what transconductance means. All right. And here, let's look at even ones from, say, 1 volts to 6 volts. Your drain current change from 0 to 240, 240 amp, right? So your transconductance is less than 200. Then is that good or bad? And so that's the measure of your device. At the end of the day, this is what we want. We want very small gate voltage change and induce very large direct current change. And that means that you can control very nicely, right? If you say 1 volt, I'll give you 100 milliamp change. Oh, that'd be nice. I mean, it's better than this one. See? So that's what it means by transconductance. When you look at the device, this is what value you look at. This value need to be as high as possible. And as means Siemens. It's just a unit of a GN. And usually when we devise, when we make this on and off, we will try to uh, insert many weird layers. Okay, here you inserted a I-L-GaN layer. Okay, your P-L-GaN is here, and then you add something here. You add a P-GaN layer here. Why is that? Initially, remember, we look at this graph. We could do P-GaN all the way up, or you could do L-GaN all the way up. You do the same thing. You could do that, right? You could change this doping to P-GaN and change that too. You could do that. So what's wrong with that? Why you need to add sometimes you need to add an intrinsic L-GaN layer? Well, intrinsic means undoped. And the reason being the interface is not friendly. That's because the defect center here at the interface. So people use intrinsic layer to mitigate that. And P usually you have Mg inside. And the Mg inside, see here, the Mg inside is P is very close to the conduction, the valence band. You can go very high. As high as you can is closer. If you do low doping is here. If you do high doping, it will be here. And how do you dope it? And that's a technology question. That's a process related question, right? And then are they all activate? Well, that's a good question. You could dope it, but sometimes it will not activate. Activate means that the magnesium has to be sitting inside a proper position, inside L-GaN, inside aluminum gallium, right? That's what it means. You cannot sit elsewhere. If you sit elsewhere, for example, a little bit away, it won't work, okay? So these are process-related questions. So this is added because the process concerned that you need to be kind of a fixed interface, all right? That's what I try to say. And doping, how do you dope it properly? Here, there are two types of doping. Very high doping, very low doping with linear, or very high doping. You could do either way. All these, uh, all these are in a way that's trying to fix it. Okay. All these are, or why you straight line or curve. All these are actually depends on how you want to this way to look like. All right. This is what it should look like. You This is the low doping make you bend a little bit off, and high doping make that bend more. And this way is always depends exactly what you need to have. And these are all from simulation. And this is one of the paper described. If you take a doping profile, your bending at the east edge. This is the results. Okay. And whether that's going to work for you, you have to run the device simulations. Okay. Then go back to let's go to the process related question. How do you make them? How do you make them? How do you fabricate this kind of head, this head here? Well, initially it was all L-GaN, right? Okay. Here I give examples. It's called this type of process called selective etch. You etch P-GaN. See in this example, you have the head, the P-GaN the P GaN and you want to etch against the PL GaN. And here, remember, you have the L GaN here. If you put a P GaN here, you can never form this. You can never form this one because if you have P GaN on top of GaN, we're gonna etch stop. When you apply a gas, you can only time it to stop at some place. And here, if you put L-GaN here, you have different element here. Then you can stop at these positions. This is called etch stop layer. And what kind of chemical are you going to use? Here you use all kinds of chlorine-related compound. So why you use chlorine? Can you use other compound? Oh, yes, you can. But it turns out the aluminum chloride and gallium chloride, they are very volatile and they are easy to handle. How about fluorine? Fluorine is good. You could do that too. But fluorine has a lot of troubles because fluorine are a lot more corrosive than chlorine. So that's the reason people prefer to use chlorine if they can. How about wet etch? Well, yes, you could do that too. For example, for SIGI, for silicon, if you want to selectively etch SIGI against silicon or vice versa, you can use TMA etch, this chemical that will selectively etch. All right, it will not touch germanium pretty much. And then digital wet etch. Okay, here is digital wet etch. Or 3.5 that people have studied a lot. And then you could go to these chemistries that I could that I have other topic cover that as well. So these are process-related questions. I give you examples. Selected wet edge, is dry edge or wet edge. You can see that this is dry edge. Okay. Use this chemical composition. You can select the edge, silicon nitride against silicon oxide. So you could go to here. Here will not touch this one. You go through here. So if you calculate this, wow, what selectivity? 260. All right. And then over what's it? This is 260. You go 260. Imagine if this is 20, then it's more than factor of 20. Selectivity is very high. And for the InGas, HCl can do that, right? At some temperature, right? Here, for example, the selectivity for InGas, InOS versus gallium arsenide for 400 degrees Celsius at CO at CCM, wow, it's two order magnitude difference. So you want a selective etch InOS versus gallium arsenide, you could use HCl. All these are examples. All right. All the examples that you could use. Here is chlorine based. These are all chlorine based. This is chlorine based. So getting more and more complex. In the GA structure, they had the same problem as well. It's not only you could etch inside, you have to etch a very vertical profile. You cannot etch this way. If you etch this way, that's not going to be good. That's useless. And here, wow, it's pretty vertical. These are nice. So this chemistry worked very well. Okay. Now, so you know how to do it. And this is exactly what Panasonic did. They began split into two portions. Okay. And then you have the insertion of the intrinsic layer, okay, away from your IGN layer. This is for edge stop. And then you put you split the hybrid. That's what you call hybrid. The gate, PGAN, and then the gate, and then on the drain, you put it there too. So why you want to do that? Well, it turns out that the drain here keep out some holes, and these holes will cover up your defect here. Your defect is next charge, so you throw in some holes to cover it up. So it's a mitigation strategy, and it worked well to the say it's pretty good. Okay. So at the end of the day, this is what it can do. It could 600 volts. It could here you could do 600 volt. You could control 20 amp, 13 amp. It's good numbers, and very fast. And then here, the peak difference here, see, this is 300 nanosecond. And here is like, I would say 30 nanosecond, reasonably good values. So the peak can control very nicely. So by adding on the process side, physically you add another drain, and this drain supply some kind of a hole, inject some holes, and that hole let the charge, the defect charge, eat it. You feed it. You feed it in a way that you could now you can control your gain nicely. You won't see that the current collapse on it. So this is the beauty of it. Okay. Here, the pecan here, you make it in a way so that you could control in a way so you could make it enhanced mode. And then this one you could use in a drain to make it uh, avoid the current collapse issues. That's so you have two birds killing two stones. Okay, and so the result is that. So this is beautiful. This is simplified version of that. As we explained before, silicon 111, and you have aluminum nitride, and then you have the super lattice, blah blah blah, and you come up with this LGAN intrinsic, and then you have PGAN, and then you have the you could solve. You use this one, the hybrid, to solve the current collapse, and use a recess gate to to have a better control of here. Why you want to use? By the way, why you want to have a recess gate? The reason being in that is the LGAN here could be too thick. And then if it's too thick, you cannot control it. You cannot see it, right? So you have to go near your channel. This is your channel, your 2D gas, right? So you cannot make it too far away. You have to recess it. All these, all these actually cost you money. It's not an easy job. By the end of the day, this is what you're gonna see. Wow, nice. Your VT, all right, ship from 0 to 1.3 volts. That's nice. Okay. So this is at the end of the day what they do. Well, is that good enough? No. There are more information I'd like to share with you. Additional but crucial discussions. Okay. Here is another concern that need to be addressed by the process. It's called sigma VT. Sigma VT means that what is your VT control of your actual device, right? And then the meeting spec is crucial before HBM. HBM means high volume manufacturing. Large sigma, large delta VT variation has very serious side effect because if you move VT greater than 0, the delta VT means that your V gate is weaker now in effect because the overdrive is VGS minus VT, right? This is your overdrive. Your VT increases, then the overdrive decreases. Overdrive decreases mean your drain current reduces, right? Yeah. And then if your VT decreases, your leakage increases, right? At the same time. So that's the dilemma. And there's a spec. The upper limit of the gate overdrive and it's for long. So this VT gonna drip. So for every device, everything gonna drip. But you had to control in a way that long-term forward gate reliability is the overdrive need to be less than 7 volts. And the maximum tolerance for the gate ringing as a turn on is less than 10 volts. And these are all the spec, 7, 10 volts. Okay, is that a big deal? It is a big deal. Okay. And then because for these devices to work, there's many weird things happen. One of the things is hysteresis, meaning that the voltage go in a positive direction and then return is sometimes form a loop. That's not what you want. This is not what you want. you have to be in the same place, right? Coming back and coming back the same line. If you're not, that's hysteresis. That means your VT shifted here. Okay, here. The VT shifted. And that's not what you want. And how big the shift? Here, if you look at the graph, it's like a couple volts. Is that good? Well, you look at the silicon CMOS. The hysteresis limit is less than 10 millivolts. And here you have what? Couple of volts. Well, that's the problem with the gallium nitride devices, right? So that's the problem. And that's one. How about the Panasonic devices? These are all hunky-dory, pretty good, but it turned out that it's not good enough. The reason being that they find out they did the device on across the wafer, the variability, see the threshold voltage change. Wow, the spread. This spread is huge from 1.3 volts, as we saw here. Remember, they did a very nice job. One device, okay, 1.3 volts. Wow. Okay. Initially, it is 1.2, 1.3 volts here. But the radial distribution of the wafer, okay, from 0 to even 70 millimeter, it spreads. This is the concern, right? Here has no spreads. But away from the center of the wafer, you have couple volt spreads, isn't it? You have 1.5 volts and then to 2.2 volts, for example. That meaning that your dry current is much less than you thought across the wafer. How can you sell a customer with that? The customer, if they pick up, if you sell a device, it's at the edge of the wafer, and the VT is 2.0 volt, and then you tell them it's 1.3 volts, then the current obtained will be much far less than you said, right? And then so that's a problem. So how do you solve that? Okay, you solve that by, well, why is that? By the way, it turns out the defect. When you form this layer of peak and recess, you have a defect. Across the wafer, the edge is not the same in the center of the wafer to the edge of the wafer. Right? That's a problem. Edge is not easy. Sometimes maybe you have more damage at the edge of the wafer. The question you ask is that, can you solve that problem? Well, they try to solve the problem, but could not make it work. Okay, for any given reason. So what is okay? I cannot solve my edge. So what do I do? So what they did is that they form a new layer. So they say, okay, before you deposit the pecan, let's do this. Let's make this layer a regrowth, TRG, through recess, regrowth layer. Once you recess it, to cure the damage from the edge, they did another epi. That is, wow, costly, right? Which means another process. You go to another chamber and you do repeat your IL-GaN process to clean up the damage here. And then you put this your pecan there and patch it afterwards. So that's what you do. You cannot solve the edge problem, but they eventually, with this regrowth gate, the problem solved. The sigma changed from 229 to 63. Okay, fair. All right. So that's what I did. And let's talk about the DIP impact to VT shift. For the 3 nanometer silicon CMOS, I do that because it's a reference. I'm going to compare that to the gallium nitride. Suppose you have a 0.1% on the visual defect, a call, and then you put that number to see how much VT shift can I get. Through this calculation, I've done this many times in my other device calculations. Pretty much, I assume that the device has one 1 nanometer CET, which is a 3.4 microfarad per centimeter squared. And then the 1% defect is this is times 0.1 times 0.01 times this, right? So which is 0.001 times 6.78 times 10 to 14, which is the silicon silicon surface density. Then you got 10 to the 11. And then divide that, boop, you got 32 nanometers. Is that good? Is that good? Well, barely make it because silicon CMOS limit of VDC is 50 millivolts. And you have one defect. I mean, not one defect, 0.1% defect. You got this. It means that how uh, how important the surface density, defect density is to a silicon device, right? If you put a number into gallium nitride, right, and then use thick oxide, okay, three nanometer CD, actually should be less. Then put the same thing here, same calculation, you got 4.2 volts. Wow, right? And this means that, and here is that interfacial layer, without interfacial layer, you want to fix it, right? You want to fix the problem. And this is how big a difference is. And this example shows that the defect density, the surface morphology change. Okay. It changed from the 3E7 to 5E18. If I use that number here, I use this 5E18 number here with this 3 nanometer CET, and this is the voltage I get, 4.2 volts. Okay. That's how bad it is can be. All right. So they mean this reveal how important that the interfacial, that the surface had to be repaired. Here we repaired the smoothness, but here is just a defect. Here they make it less rough. See, here is wow, rough, and here you make it very flat. Nice. Okay. Even the physical change could change your defect by 2 order of magnitude. That's what gallium nitride people saw. Okay. And before I leave you, there are more discussion. The DIT concept versus uh, the formula level pinning is very difficult to explain. The reason being it had reduced the concept by charge neutrality levels. For in a semiconductor side, we don't have this curve. We have this. Let's call formula. There's a band gap here. But for a free surface, there's no band gap. Therefore, the charge neutrality level is a continuous curve. The energy curve on a surface, on a free surface, is continuous. But on a semiconductor, in the inside semiconductor, the energy state for electron has a energy band gap. That's where the EG coming from, right? But that's not happening for the surface. And so when these two interact put together, what happens? That's the big questions. And here you can see that the surface state, okay, the DIT, is a negative charge. Or these are complex concepts to understand from the charge and charge level. And I put that explanation in my other video. If you're interested, please go there. I'm creating another video, try to give a deeper understanding in the charge and charge level energy calculations. And that's going to be interesting. Okay. So I'm not going to go detail here. I'm just saying because the interface stays so difficult to understand. But everybody in the world try to mitigate that, try to say, I'm going to pacify my DIT to get my device performance back. If you look at my discussion on the silicon carbide devices, you can see that the silicon carbide intrinsic mobility is close to 1,000. But in reality, every device in this world is less than 50. You lost 95% of your mobility. Okay. And that's how severe this problem is. It kill your device, it make your mobility very low. And that's the problem even for gallium nitride. Okay. Now, the important thing, the previous important thing is the interface state not just kill your mobility, but also shift your VT to place you don't want to. Initially, I want to go to enhanced mode, but well, it's 1.2 volts, right? You did it. But if the defect is bad, you could have a change of 4.2 volts, which bring you back. We go to the other side or make it worse or make it more positive or negative. Go to a direction you don't want to by a couple of defects, by 11 uh, centimeter squared defect. So this tells you that the importance of interfacial defect can change your VT so much and make your nightmare. So that brings you to this graph. So if you look at the cum plot, it's cumulative plot or cum plot or CDF. If you look at the publication, say, oh, this is what I saw, VT distribution, or your factory device. And then you look at some people publish, oh, this is what I saw. Which one's better and why? And this one, pretty bad because it bends. Here is a straight line. It's good. Okay. And why is that? Why this bends is bad and this no bend is good? Okay, let me explain that with a simple cumulative the CDF with a simple CDF concept. Okay, a CDF means cumulative the distribution functions. It's a sum of PDF. What I meant is that if you throw a dice, probably your dice for each dot, 1 to 6, is the same for all sides. 1, 2, everybody is 1, 6, right? And the cumulative means that you're summing your sum of the previous one, including yourself. So CDF 1 is point, say, 1/6. I mean, 1/6. GDF 2 means that 1 plus 2, right? See here, they are the same here. Then you step up. So here, and then you do continuously, you have smooth functions, right? And so Q plot on the top right, every plane has fair and random. So everybody got 1/6. Then your Q plot gonna be smoothly going up steadily. Now imagine someone is cheating. They make it in a way that there's no 3 and 4. Okay, there's no 3 and 4. The dice has no 3 and 4. Every time it come out is 1, 2, 5, 6 with the same probability. Then the probability of 1 is 0.25. So what happened to a Q plot then? A Q plot will start have a plateau. See here? Q plot CDF 1 is PMF 1. 2, right? It go up. It's nice what you see, 0.5, this is 0.25. Okay, this is 0.25. 0.5. But for the third, it's the same as 2 because the third is gone. So it will be same 0.5. And then CDF 4 is the sum of previous 4 is the same as 2. So you have a plateau show up and then go back to up again. And this means that this is what happened. This means that somebody is stealing your dice, meaning that there's an unknown defect mechanism at work that you don't know. Okay. So this is I call a systematic error, which means that if you look at the Q plot, right, and this is an actual device, okay, this is a SM, SRAM devices. You can see that the red one go flat before it go back up. And this is where Q plot show you that there is a defect mode that you don't know. A defect mode is a systematic error. A cheater is a systematic error. And then it needs to remove to go back to the right place. Right? It needs to go back to here. So this means that your device is something wrong. You need to fix it in a way so it will go back up, okay, to a one straight line with a log to a linear mode. Right? This is a log to a linear mode. I mean, this is a log. This is a log scale, the scale log. Okay, and this is a linear mode. It should go back up this way. Instead, it bends and go this way, meaning that there's an unknown systematic error. Systematic happened here. We don't know what it is though, because somebody is stealing your die. This is a defect. It kills you absorb some, your device on something and make your process not not uniform, not in the right order, and that's the cheaters. And this is what you need to know, what you need to resolve as a process guy, okay, as a device guy. When you see that, you go to the process guy, say, hey, this systematic error in your process, go fix it. The device guy will help, the process guy will help, will help you, of course, but that's your job as a device guy, right? So, okay, so this is what I've been given in this class. The emo began by do a hybrid. This Panasonic did. Somebody else did it. Something in the scheme. Yeah, I think so. You talk to Quavo, if you talk to other Infineon, they may have other ideas. But here I introduce your ideas and I show you how you study with the connected papers and Perplexity AI and give you some simple statistical tool you can understand your VT signals. So to make a CVT go to the enhanced mode is not enough. You need to make it uniform across. You make your VT variability small below your reliability spec. That's what you need to do. It's a challenging thing, but that's it. It is what it is. C'est la vie. Okay. All right. Thank you. Thank you, boss. This is all I talk.